In this video, we're going to be talking about differentials, which just gives us a way of talking about a change in our variables, whether we're talking about a change in our input variables or a change in our output variables. And usually we're looking for a connection between them. How does changing the input induce a change in the output? Okay, so let's just suppose I have z as a function of two variables. Of course, this generalizes to functions of three variables as well. And I've got some point p naught in the domain. So I've written up here the formula that we have for our local linear approximation. Let's go ahead and suppose that f is a differentiable function so that this would earn that name. Okay, if I'm working with the actual function and I'm talking about a change in my variables, I would talk about the change in x as being delta x and the change in y as being delta y. And these would just be the signed distance between a point x and the point x naught that we're talking about here. And delta y would just be the signed distance between a new y value and the y value at my special point p naught. Okay? And then delta z would be the difference in the z values for those points. So if I called up my point p, my arbitrary point x naught, delta z is just f of p minus f of p naught. Notice with all of them, the order of subtraction is consistent. We're always subtracting the values corresponding to our reference point p naught. Okay, excellent. So basically we'd be looking at, hey, if I move a little ways away, usually we'd want these changes to be relatively small. If I move a little ways away from p naught, how does that affect the output of my function? Now I can ask that same question for the linear function that we're using to approximate our function. And that's why we generally are going to want to keep these changes relatively small, because the linear approximation does a good job of approximating the function at and near p naught, but the linear approximation may do a terrible job of approximating the function if we go too far away. Okay, so if I'm talking about the change in the linear function, that's when I use my differentials. So we would have dx and dy and dz. And these are basically just representing amounts of change in the linear function. I want to think of these guys as variables. So these guys, dx and dy, would be my independent variables. dz, which will represent L of p minus L of p naught, it will just be the change in the output of this linear function. So it's playing the same role that delta z is playing over here. With f, it's playing that same role with L. Okay. This I'm going to think of as my dependent variable. Dependent variable. So I'm saying this, the value of this depends on this. So if I control how much I change x and y, that will tell me how much z is changing on this function here. The same thing is actually true here. If I control how much I change x and y, if I control delta x and delta y, that's going to determine what delta z is as well. Okay? All right, but since these are independent variables, there are input variables, we can choose what to make them. So generally what we're going to do is we're going to set these equal to our delta x and our delta y. Because if dx is equal to delta x and dy is equal to delta y, if I allow x and y to change the same for both f and L, then I can say that dz will approximate delta z. The amount that my tangent plane changes will be approximately the amount that the function changes. And of course, if I had a function of three variables, then dz would join dx and dy in being an independent variable, and dw would be my output variable. And we'd be using dw to approximate delta z. let's just take a look at an example to see why that might be useful. We're basically just saying linear functions are easy to work with, other functions aren't necessarily. So let's take a look at the example where f of xy is x squared over y cubed. Let's let p naught be the point 2, 1. Let's let delta x equal 0.1 and delta y equal negative 0.2. So notice these changes in x and y, and of course the corresponding changes in z, are signed quantities. When delta x is positive, that's telling me that we're going to make x bigger by 0.1, and delta y being negative here tells me that we're going to make our y value smaller by 0.2. So essentially, that was another way of saying we're looking at the point P being 2.1, 0.8. Okay. All right. Now, I could certainly calculate delta z if I wanted to. Delta z would simply be f at 2.1, 0.8 minus f at 2.1. Now, f at 2.1 is very easy to calculate. That's just 2 squared over 1 cubed. That's going to give me 4. Here, this would be 2.1 squared over 0.8 cubed. Not the end of the world. I could do that. But that's a little bit tedious, particularly if I'm doing it by hand. That's where differentials are nice, because with differentials, I'm working with this linear function, and all I'm going to have to do is multiply and add. Okay. And here, this was a very simple function because I just combined x's and y's using arithmetic. If I start throwing in exponentials and trig functions and logs and things like that, it becomes very difficult sometimes to evaluate the change in the output function directly by hand without the aid of technology. Okay, so I'm going to say that delta z can be approximated by dz, by that differential. Sometimes this is called the total differential. Sometimes, and this is what your book usually calls it in the homework, it's just the differential for f. Okay. And I know I defined dz as just being L of p minus L of p naught. That is what it is. It's the change in the linear function. But that's almost never the formula that I'm going to use for it, because if we remember when we created our formula for our linear approximation, we said the z value on our tangent plane was going to be the z value at the point of tangency plus the change in z. Now, f and L agree at p naught. So this is the same as L of p minus f of p naught. That's just this part of things. The change in z, that's dz. Now, I actually referred to that in an earlier video, and I probably shouldn't have, because at that point, L was a candidate for the tangent plane. If L is the tangent plane, if we have a differentiable function, I would call this portion dz. We really don't talk about differentials if we don't have a differentiable function. Okay, so if your function isn't differentiable, we won't talk about differentials. But assuming that your function is differentiable, and certainly this one is, then this portion, the gradient dotted with the change vector, is just my differential for that function. Okay, so the formula that I'm generally going to use is that it's the gradient of f dotted with, now this change vector, notice x minus x naught, that's our delta x, but we were going to set dx equal to delta x. So x minus x naught, I can denote as delta x when I'm talking about f, but I can denote that same quantity as dx when I'm talking about L. Same thing for y minus y naught. That was the change in y, but we're choosing to set our independent differential, dy, equal to delta y. So we're really dotting with dx dy. Okay. All right. Now, of course, I wanted to evaluate this at a particular point. So this is sort of the generic formula to come up with a formula for the differential for the function. If I want to evaluate the differential for this function at this point with these particular changes in things, then what I'm going to be looking at is the gradient of f at 2, 1 dotted with 0.1, negative 0.2. Okay, so let's go ahead and calculate this. The gradient of f is just f sub x comma f sub y. So let's see, that's going to be 2x over y cubed. 1 over y cubed is just a constant. Now, I can write this as x squared y to the negative 3. That'll help me in taking the partial with respect to y. That's going to give me negative 3 copies of x squared, and then I would get y to the negative 4th, which I'm just going to write as y to the 4th on bottom. Okay. The gradient of f at the point 2, 1 is, let's see, that's going to be 4 over 1 is 4. That's going to be negative 12 over 1 is negative 12. Okay. So I can see then that what we've got is that dz is simply 4, negative 12, dotted with 0.1, negative 0.2. All right, so that's going to give me 0.4 minus times a minus is going to give me a plus. So plus 2.4, that's going to give me 2.8. So here I would estimate that delta z was approximately equal to 2.8. And I was able to do all of that by hand. It's a very simple calculation, whereas if I need something more exact, I would probably want to use technology with most functions, or it would just be time consuming to do by hand, which I could have done with this one.